See, I have a 5-sided figure like this. It is kept in a magnetic field which is directed along the positive direction of the x-axis. The dimensions of this are given, sides of this. The field as it is 0.4 Tesla. Now the problem is the field is increased from 0.4 Tesla to 0.45 Tesla. Okay? The question is, what is the change in flux? What is the change in flux through the phase A, B, C, D? Through the phase B, C, F? Through the phase A, B, F, E? First you tell me, what is the change in flux through the phase A, B, C, D? Come on. How do you do this? What is the change in the flux when the field increases from 0.4 Tesla to 0.45 Tesla? What is the change in the flux through the phase A, B, C, D? How do you find? First, find the initial flux when the field is this much. Initial flux is what? B dot A, which is B into A into cosine of the angle between B and A. Right? You know what is A, what is B, what is theta. Substitute and tell me what is the initial flux. What's the initial flux? So simple. How much? Minus? No. What is the initial flux? See, what is B? 0.4. What is A? A is length into breadth, correct? No? This is same as this, no? 3 into 3, which is 9 into cosine of the angle between vector B and area vector. 180, because we take the area vector from inside to outside perpendicular to the surface. B vector is in this direction, A vector angle between them is 180. So how much it comes to? How much it comes to? Minus 3.6 Weber. Okay, what is the final flux? What is the final flux? What is the final flux? Minus? What is the change in flux therefore? What is the change in flux? Phi I is initial, phi is final. What is change in flux? 0. Yes, that's the right answer. 0.45 Weber is the change in flux. Have you understood this? Tell me anyone who has not understood. Okay, what is the change in flux through the phase BCF? By, theta is 90 degree, angle between vector B and vector A is 90, cos 90 is 0, correct. What is the change in flux through the phase A, B, F, E? Come on. Change in flux. In fact, in the first case, remember it is minus, because phi F is smaller than phi I, no? In the first case, you follow out, first case it is minus. Second case 0. Third case is, what is the change in the flux? No. Yes, 0.45. How do you get it? First, see what is the flux through this? What is the flux through this? Flux through this is area of this into field. The field is in this direction. You have to consider B dot A, no? A vector is normal to this area. B vector is in this direction. What is the angle between the two? Call it theta. That theta is same as this theta, no? Because this is perpendicular to this. This is perpendicular to this. If this is 3, this is 4, this side must be 5. So what is cos theta? 3 by 5, no? So what is the initial flux there? Find out. B into A. What is A? A is 5 into 3 into initially it is here cos theta, which is 0.4 into 15 into 3 by how much it comes to, man? 3.6 Weber. What is phi f? In the place of 0.4 you have to put 0.45. So how much it comes to? Then find the difference. Find the difference. How much it comes to? 0. It comes to 0.45. Yes. Now in the same problem, follow me carefully. In the same problem, he says he lifts this such that the face ABEF becomes parallel to the XZ plane. Have you understood? He lifts this side so that ABFE becomes parallel to the XZ plane. What is the change in flux? Come on. Tell me what is the change in flux? How much? Final flux minus initial flux. Correct now? What is final flux? 0, because angle between B and A is 90. No. What is initial flux? We have already calculated it. How much? 3.6. So what is the change in flux? Minus 3.6 Weber. Exactly. Minus 3.6 Weber. Draw this figure. A long straight wire carries a current of 2 amps. A long straight wire carries a current of 2 amps. A small circular coil of diameter 0.2 meter of diameter 0.2 meter is located with its center a small circular coil of diameter 0.2 meter is located with its center at a distance of 5 meter from the wire. at a distance of 5 meters from the wire. Assuming the field within the coil to be uniform, and has a value equal to its value at the center, calculate one flux in the coil. Two, if the current in the long wire decreases to 1.5 amp, in 0.003 seconds, what average EMF is induced in the coil? Three, what is the direction of the induced current? Because induced current in the coil, remember. What is the direction of the induced current in the coil? First, tell me how to find the flux in the coil. Flux through the coil is? Flux through this coil, how do you get? First find the B. He says the field here throughout is uniform, having a value equal to the field at the center. Find the field at this location due to the current in this. How much? Mu naught I by 2 pi r. Once you know that field, multiply it by the area of the coil. That will give you flux. No, come on, finish it and get me the answer. B dot A is BA there, you know. What's the answer you get? Calculate it and get me the answer. Flux through the coil is? Four. Mu naught I by 2 pi r into pi r square, where that r that I say is the radius of the circle. And when I say mu naught I by 2 pi r, that r is the distance of the center of the circle from this. How much? How much it comes to? Not 25, just check.
1.2.
2.51 into 10 to the power of minus 9 Weber, correct. This is directed into the paper, of course. So, flux through the coil is 2.51 into 10 to the power of minus 9 of a Weber. Next he says, if the current in the long wire decreases to 1.5 amps in 0.003 seconds, what average EMF is induced in the coil? What you now do is, for this current, what is the field at that point? What is the flux now? This final flux minus initial flux, change in flux, delta phi, that divided by delta t, which he has given it as 0.003 seconds. That's the induced EMF. No, find out. How much you get? No. What was the change in flux that you got? Tell me. No. See, initial flux was when the current was 2 amp. What was the flux? 2.51 into 10 to the power of minus 9 Weber. When the current was changed to 1.5 amp, what is the new flux that you got? 1.88 into 10 to the power of minus 9 Weber. So, what is the change in the flux? Final flux minus initial delta phi is minus how much? 6.3 into 10 to the power of minus 10. Correct? So, what is the EMF induced? Delta phi by delta t. Delta t is 0.003. 6.3 into 10 to the power of minus 10 divided by 0.003 is 2.1 into 10 to the power of minus 7 volt. Are you not getting? Answer is 2.1 into 10 to the power of minus 7 volt. Correct now? Now, what is the direction of the induced current in the coil? Tell me, is it clockwise or anti-clockwise? Tell me. It is? Yes. Next. Use Lenz's law. A circular coil of radius 0.2 meter. A circular coil of radius 0.2 meter is in a uniform field. A circular coil of radius 0.2 meter is in a uniform field. B is equal to 0.6 Tesla. B is equal to 0.6 Tesla. Coming out of the paper as shown in the figure. Coming out of the paper as shown in the figure. If in a time 0.002 seconds the circle is deformed into a square. The circle is deformed into a square with the same perimeter. With the same perimeter, find the EMF induced in the coil. Find the EMF induced in the coil and also the direction of induced current. And also the direction of induced current. What do you do? Find the area of this. Okay. multiplied by strength of the field, initial flux. Find the area of this. For that, first you should know the length of the side. For that, he has given the condition, perimeter is the same. Find the final flux, change in flux, delta phi by delta t, that will give you the induced EMF. And then use Lenz's law to find the direction of the induced current. Come on, do it. Okay, what's the answer for the earlier one? Induced EMF is? No. Minus 8 point, how much? Minus 8.1 volt. Why? Area decreases, final flux is less than the initial flux, no. So, final flux minus initial flux is negative, no? Correct? What is the direction of the induced current? Anti-clockwise, exactly. Direction of the induced current is anti-clockwise. Apply Lenz's law. Draw that figure. Take this problem as home assignment problem. Come on. Try this at home. A triangular coil of dimensions shown, a triangular coil of dimensions shown is placed in a magnetic field of 0.2 Tesla. Is placed in a magnetic field of 0.2 Tesla. Tell me what is the direction of the field now? Directed into the paper. Directed into the paper. Triangle collapses to zero area. The triangle collapses to zero area in a time of 4 into 10 to the power of minus 2 seconds. 4 into 10 to the power of minus 2 seconds. What average EMF is induced in the coil? What average EMF is induced in the coil? And in which direction? And in which direction the induced current will flow? And in which direction induced current will flow? Try this, I will give you the answer. Check whether you get this answer. The induced EMF is 21.9 volts. And the direction of the induced current is ABC. Direction of the induced current is ABC. Next, draw this figure. A circular coil of radius 2.1 meter carries a clockwise current of 2 amps as shown in the figure. A small circular coil at the center of the outside coil has a radius of 0.011 meter. 0.011 meter. Assume that the magnetic field produced by the outer coil is uniform within the area of the inner coil. The current in the outer coil increases at a steady rate of 3 into 10 to the power of minus 2 ampere per second. 3 into 10 to the power of minus 2 ampere per second. Find the EMF induced in the inner coil. Come on. How you do it? Find the field at the center of the inner coil produced by the current in the outer coil. Multiply it by area, that will give you the flux. Correct now? Then find the rate of change of flux, that is the induced EMF. Come on. Get me the answer. Got the answer? Ten to the power of minus. Yes, that's the right answer. 3.41 in 10 to the power of minus 12 volt. See, what is the field at the center of the outer coil? Mu naught I by 2R. So, what is the flux? B dot A, which is BA, which is mu naught I by 2R into A. What is the induced EMF? Magnitude of that is d phi by, which is here you can see mu naught A by 2R. They are not changing with the time. What changes is I. Current is changing with the time. He has given the rate of change of current as how much? 3 into 10 to the power of minus 2. Di by dt is that value, no? Clear? See, he says the current is increasing at the steady rate, di by, that is di by dt, 3 into 10 to the power of minus 2. Substitute there. Any doubt? Draw that figure. Hurry up. See, there is a bar here which is moving along this triangular rails. It moves with certain velocity. At certain time instant, say t naught, it is at a distance 6 meter from this point. He has asked us to calculate the induced EMF at other time instants. A bar is moving along a triangular track. A bar is moving along a triangular track as shown with a velocity of 8 meters per second. The bar is 6 meters from the start of the track. The bar is 6 meters from the start of the track. At t is equal to t naught. The bar is 6 meters from the start of the track at t is equal to t naught. There is a uniform magnetic field. There is a uniform magnetic field of 0.8 Tesla. 0.8 Tesla out of the paper in the entire region. What is the average EMF induced in this circuit? What is the average EMF induced in the circuit between 1 t equal to t naught and t equal to t naught plus 2 seconds, 2 t equal to t naught and t is equal to t naught plus 1 second, 3 t is equal to t naught plus t is equal to t naught plus 0.25 second, 4 T is equal to T naught plus T is equal to T naught and T is equal to T naught plus 0.1 second. Okay. 5. In which direction does the induced current flow? In which direction does the induced current will flow? Okay. Now, tell me how to do this. First part we will see, the others you try it at home. Tell me how to do this. Area of this triangle is how much? This has x you mean to say. He has given it as 6 meters. So take this as x. X by 6 equal to tan 30. So you can find out what is x. Once you know this and this, you can calculate the area. Once you know the area, you can calculate the initial flux. Clear? Now, this is at t is equal to t naught. He is asking at t is equal to t naught plus 2 seconds. So, at that instant t naught plus 2 seconds, what is the area you have to find? Here the flux changes because the area is changing. Field remains the same, remember it. So, how do you find? At t is equal to t naught plus 2 seconds, what are the sides of the triangle? You can find out. How? It moves with a velocity 8, he says. Every second it covers 8 meters. So, at t naught plus 2 seconds, how much it should be? This 6 plus 8 plus 8. How much? 22. If you know this as 22, then you can calculate what is x. Because using that x by 22 equal to tan 30, you can calculate that x. So, calculate this final area multiplied by field, that will give you the final flux. So, what is the change in the flux? From that, can't you find out? Clear? Will you attempt that? Okay, do that. Now, so far we have seen problems, variety of problems we saw on how to calculate the flux through an area. Okay, how to calculate the, for example, change in flux, how to calculate the induced EMF. Now we will take up motional EMF produced in a conductor when it is moving in a magnetic field. We will first take up a simple problem. There is a magnetic field directed, uniform field directed out of the plane of the board. Okay, there is a metal frame P, Q, R, S moving with a velocity v in this field. What is the EMF induced in this loop? Can you tell me how to do this? What is the EMF induced in this loop? Zero. How could you say that? We will have to work it out. No, it extends. It's uniform over the entire area, and in the region in which it is moving, the field is uniform. Now, what you do is, follow me carefully, what is the EMF induced in PQ? Zero, because L and V are parallel, theta is 0, correct? No, EMF induced in this is 0. EMF induced in this is 0. There is EMF induced in this, EMF induced in this. Now what is the EMF induced in this? BLV. We have worked it out now. When half the frame, say part of the frame is inside, part of the frame is outside, have we not worked it out? Induced EMF is BLV, we calculated the current, we calculated the power. Don't you remember? In one of our earlier classes? BLV. Follow me. When this is moving, there is an EMF BLV induced in which direction? This is a closed loop, so a current is flowing. In which direction? In that direction EMF is induced. Make use of right hand rule. Do you remember? Forefinger in, not the left hand rule, that is used to find the direction of the force acting on a current carrying conductor moving in a magnetic field. Here the conductor is moving in a magnetic field. What is the direction of the current induced? Given by, of course, when these are all perpendicular to each other, forefinger in the direction of the field, thumb in the direction of motion, middle finger will give you the direction of the induced EMF. This portion therefore acts as the source of EMF. It acts like a battery, no? And inside a battery, current flows from negative to positive. The induced current is in this direction, so this should be positive, this should be negative. Will you agree? Same thing should be true on this portion also, no? Right? So this is also. So what is the total EMF induced in this loop? EMF induced in PQ plus EMF induced in QR plus EMF induced in RS plus EMF induced in SP. EMF induced in PQ is 0, in QR is BLV, in RS is 0, here minus BLV, which is 0. Do you agree? Okay. Have you not worked it out and part of the, we will take it then, we will work it out. EMF induced in a frame moving out of a uniform magnetic field. If you have not worked it out, I think I worked it out for the other batch. EMF induced in a frame moving out of a uniform magnetic field. So the field is confined within this region. The field is confined within this region. This is the boundary of the field. So you have a frame being pulled in this direction. I'll call this frame A, B, C, D, say. Okay, it is pulled in this direction with the at any time instant, let this be X, let this be L, say. Okay. As before, you can see there is no EMF induced in this, correct? No EMF induced in this. There should be EMF induced in this. What about this? it's not cutting the lines of force, correct now? Okay. At certain time instant, what is the flux linked with this loop? It is strength of the field into area. What is area within this? L into X. So, what is the magnitude of the induced EMF? d phi by dt, which is d by dt of B L X. B is not changing with time, L is not changing with time, X is changing with time, dx by dt is V, induced EMF. You see, the interesting thing is, there we saw when the entire loop is within the field, the two, in these two EMFs are induced with a tendency to drive equal currents in the opposite direction. So, net EMF is, there is no EMF in this, EMF in this, but there is an EMF that is induced in this portion, correct now? There is no EMF. As a result of this EMF, there is a current flowing. Will you agree? In which direction the current is flowing? You see here, this acts as a battery, it acts as a source of EMF. And you know, inside a battery, current flows from negative to, so, correct now? Okay, in which direction this current is flowing? Forefinger in the direction of the field, correct now? Thumb in the direction of motion. So, correct? What is the strength of the current? E by R, where R is the resistance of the loop. So, it is BLV by R, correct now? BLV by R. There is a current flowing in this. Now, as a result of the current flowing, you can see there is a force acting on this. What is the force acting on this side? Can you tell me? Forefinger in the direction of the field, middle finger in the direction of the current. So, use left hand rule. Forefinger in the direction of the field, middle finger in the. There is a force. How much is that force? BI L. Will you agree? Now, the interesting thing that if these two forces cancel each other because they are equal in magnitude, opposite in direction. See, there is a force coming into picture whenever you try to pull this loop out of the field, a current is induced, as a result of which a force acts which is trying to oppose. No. So, if you want to pull this out with a constant velocity, you have to apply a force on this side which is equal to this. Suppose you want to accelerate this, you have to apply a greater force. That acceleration can be found out from force divided by mass, where m is the mass of the loop, say. Okay. Now, this is the current. What is the power that is dissipated in this? It is I squared R, which is B squared L squared V squared by R. Will you agree? Will you agree? This is the power that is dissipated. Will you agree? In the resistance. Now, what power you need to supply from outside? What power that you need to supply from outside? That power is given by F dot V, which is FV, you can take it, correct now? What is F, man? B I L. What is V? What is V? The power that you have to apply from outside is F dot V. F is VIL into V. You should get it in this form. You get it in this form. Listen, listen, listen. This is B into, what is I? I is B L V by R into LV. See, you can see what power you apply, what power you supply from outside to pull it. That is appearing in the form of heat energy in the resistance of the wire. Have you understood? The magnetic field doesn't do any work on the charges because the force is always perpendicular to the velocity, but it is responsible for converting this supplied mechanical energy into electrical energy in the resistance of the wire. Have you understood this? Okay. So when the entire loop is within the field, there is no EMF induced. When part of it is within, you have this situation. Okay. Take a problem. Find the EMF induced in a straight conductor. Find the EMF induced in a straight conductor rotating with a uniform angular velocity omega in a uniform magnetic field capital V. See, this is a magnetic field applied perpendicular to the plane of the board. Okay, there is a straight conductor of length L, which is say rotating about the point O. I'll call this end say A. This is the length of this conductor. It is rotating with a uniform angular velocity omega. What is the EMF induced in this? Usual tendency is to say answer is 0 because there is no change in flux, you may think. But EMF is induced due to motional EMF it is. What you do is consider a small element of length dx at a distance x from this. What is the EMF induced in that? EMF induced in that small element is B. L is dx, correct now, into V. B into L into V. L is dx into V, but V is omega x. It's not a linear motion there, rotatory motion. So this is B omega x dx. So what is the total EMF induced in the entire rod? Integrate this from 0 to L. What is the answer? This is the EMF induced. As you can see, if omega is more, if it's going faster and faster, the EMF induced will be greater. In fact, you can put it in another way. You can write it as half B, omega can be written as 2 pi F into L squared. Will you agree? You can cancel this B into F into, what is pi L squared? Pi L squared is area that the rod sweeps as it rotates. Area that the rod sweeps as it rotates. Will you agree? Next, to find the EMF induced, in a conducting disc, to find the EMF induced in a conducting disc rotating about its axis in a magnetic field. Rotating about its axis in a magnetic field. Follow this carefully. This is a circular disc kept perpendicular to the plane of the board. The disc has a radius r. Okay? The disc is rotating about its axis with an angular velocity omega. The field is directed along the axis. The field is directed along the axis. Okay? What's the EMF induced? How do you go about? Tell me. The easiest way is, you can imagine this disc to be made up of a number of such rods that you have considered with their one end at, oh no. You consider a number of such rods of length r with their one end at O. What is the EMF induced? Half B omega r squared. Will you agree? Considering the disc to be an assembly of rods of length r with the common end located at the center, you can write EMF induced is equal to half B omega r squared. Now, this is the case when the plane of the disc is perpendicular to the direction of the field, or axis of rotation is in the direction of the field. Suppose the direction of the field makes an angle theta with the axis of rotation. If the direction of the field makes an angle theta with the axis of rotation, what can you guess about this strength of the field? It is? Yes, B cos theta omega r square. It's B cos theta omega r square. If the field actually is in the direction of say in a direction perpendicular to the axis of rotation, tell me, if the field is in a direction perpendicular to the axis of rotation, induced EMF will be 0. Induced EMF will be 0. Clear? Next, I want you to try this. I want you to try this and get me the answer. A bar of length 0.8 meters, a bar of length 0.8 meter is moving to the right, with a velocity of 500 meters per second, with a velocity of 500 meters per second, in a magnetic field of 0.3 Tesla, in a magnetic field of 0.3 Tesla directed into the paper. What is the motional EMF produced? What is the motional EMF produced? If the bar is sliding, with the same velocity along two frictionless conducting rods, connected to a resistor of 60 ohms, as shown in the figure. I will draw the figure of this. As shown in the figure, calculate one current through the resistor, 2 power absorbed by the resistor, 3 in what direction does the current flow through the bar? In what direction does the current flow through the bar? Come on, get me the answer for this. These are the two railings. This is the bar which is moving. The field is directed perpendicular to the this is moving to the right. You call this point A, you call this point B, say. Now calculate. First, motional EMF you find out. What is the motional EMF? 120? Yes. What is the current? 2 amps. Then what is the power? 240. Then he says what? In what direction does the current flow through the bar? Through the bar. Say bar is AB, no? So in which direction current is flowing? It is flowing from A to B. Clear? This is a beautiful problem. Draw this figure. This is x-axis. This is y-axis. This is z-axis. In the x-z plane, there is a circular loop. There is a circular loop lying in the xz plane. I'll call this point A, B, C, D. There is a magnetic field directed along the negative y direction. There is a magnetic field directed along the negative y direction. Initially it is kept in the xz plane, then it starts rotating this side going up. Okay, write down the circular coil in the figure. The circular coil in the figure is rotating about the x-axis. The circular coil in the figure is rotating about the x-axis with an angular velocity of 130 radians per second. 130 radians per second with the point small a, this point with point small a moving upward, with the point small a moving upward from the position shown. The coil has an area. The coil has an area of 0.24 meters square. The coil has an area of 0.24 meters square and is initially in the XZ plane. There is a uniform magnetic field capital B in the region. There is a uniform magnetic field capital B in the region of 0.25 Tesla pointing in the negative y direction. Calculate the average EMF induced in the coil. Calculate the average EMF induced in the coil during a time of 5 into 10 to the power of minus 3 seconds. I'll read the problem again. The circular coil in the figure is rotating about the x-axis with an angular velocity of 130 radians per second, with the point A moving upward from the position shown. The coil has an area of 0.24 meters squared and is initially in the XZ plane. There is a uniform magnetic field capital B in the region of strength 0.25 Tesla pointing in the negative y direction. Calculate the average EMF induced in the coil during a time 5 into 10 to the power of minus 3 of a second. Tell me how you do this. How you do this? To find the EMF, you have to calculate the change in the magnetic flux, divide it by time. To calculate the change in the magnetic flux, you should know what is final flux, what is initial flux, difference. Yes, initial flux can be known straight away because the field is perpendicular to the plane. So, area of that circle into, correct. How to find?
Angle rotated using time and omega. You can find the angle rotated.
From that.
Find the component of area vector. Then you can just find V dot A.
Exactly. See, he has given omega, no? In a time t, what is the angle swept? Omega t. Once you know that omega t, then the flux is B dot A, which is B into A into cos theta, which is cos omega t. Correct? So, initial flux you know, final flux you know, change in flux you calculate, divide it by time, that is the induced EMF. Will you try it at home? Check whether you get this answer or not. The answer that you should get is 2.4 volt. The answer that you should get is 2.4 volt. Clear?